Welcome back, class. Tonight we're going to learn about the second law of thermodynamics. Remember, the first law of thermodynamics is just a restatement of the law of conservation of energy as it applies to systems with gas. And it said that the internal energy of the gas will change whenever there's heat flow or work. And we're going to learn to apply that with the second law of thermodynamics. Now, the second law of thermodynamics deals with efficiency. So it says basically that not all of the heat that you add to a system of gas can be converted into work. So when you heat up a gas and it expands, you're not going to get as much work out of that expansion as you did the heat you put into it. And so that is the second law of thermodynamics. It deals with the efficiencies of systems with gas. And we're going to learn about these systems with gas. And we call those systems that utilize heat flow to do work, we call those things heat engines. And we're going to learn about a couple different examples of heat engines in just a moment. So heat engines convert heat to work. And this was the Industrial Revolution. When steam engines were first invented, it was the ability to boil water, create steam, have that steam expand, and do work on a piston. And that's what turned the wheels that allowed us to make ships that could go across oceans and trains that go across continents, and even industrially produce products and mill wood and things like that. So now heat engines operate at a constant temperature. Once you run the engine for a while, it's going to run at a constant temperature. This isn't true when you first turn them on, but after they've been running for a while, the temperature of that engine remains constant. So we'll see that delta U is 0, because remember, when temperature is constant, the internal energy is not changing, so delta U would be 0. So if delta U is 0 and we add work done by the system to both sides, that's going to cause work on the right to cancel out. We're going to see that the work done by the system is equal to the heat flow. Now, this heat flow is going to be the heat that's added minus the heat that's taken away from that engine, which is what we're going to see in just a moment. So there are two parts to every heat engine. There's a part where you're actually burning the fuel. We call that the high temperature reservoir. And then there's the part where that energy gets expelled to. Usually that's the outside of the engine, or the low temperature reservoir. So let's go ahead and look at some heat engines. Now here is a diagram of a heat engine. All right. So a heat engine is anything that converts heat to work. So here we see energy being added in the high temperature reservoir. Here's where we're going to burn the fuel to do work. Remember, this is a diagram. This is not an actual heat engine. This shows you the energy that's transforming. So here's where we would burn the fuel and get a certain amount of energy from burning the fuel, right here in the high temperature reservoir. And we're going to get some work done out here out of it by having that hot gas expand against a piston and do work. And then we're going to get some energy that's still expelled to the environment. So some of that heat is going to be expelled back to the environment. So the heat that you put into the engine is QH. The heat that gets exhausted to the environment is QC, heat out at the cold reservoir, and QH is the heat that's burned in the high temperature reservoir. So the amount of work done you get out of the heat engine is the difference between those two. And this is what the second law says, that only some of the energy you add to the heat engine can be converted to work. The rest is expelled as heat to the environment, the low temperature or the cold reservoir. So here's a diagram of a steam engine. Actually, this is a steam turbine. This is what we use to create electricity in most of our power plants in the United States. So here is our high temperature reservoir, the boiler, where we burn. In the United States, it's mostly coal. And when we heat up the water, it'll eventually turn to steam. And that steam will expand against a turbine and spin a turbine, just like it would spin the wheels of a steam engine. The turbine would spin the turbine, and that's what would generate electricity. Notice that a lot of that heat would get expelled to the environment. So here's our high temperature reservoir, and outside, the outside environment would be the low temperature or cold reservoir. So gasoline engines and steam engines are examples of heat engines. Okay, where we have heat flow that is used to do work. And the reason we can do that is because hot gas will expand. We're also going to learn about heat engines in reverse, like refrigerators and air conditioners, where we do the exact opposite. We do work on a gas, we compress Freon in order so that we can flow heat. And we're going to learn about that a little bit more tomorrow. So let's do an example problem. If a steam engine takes in 4,000 joules of heat from burning coal and puts out 2,500 joules of waste heat, then how much work did the steam engine do? So let's go ahead and look at our formula, and this is on your formula sheet, so there's nothing to worry about. We have that the work done is equal to the heat at the high temperature reservoir added minus the heat that's expelled at the low temperature reservoir. So QH is the heat added at the high temperature, and QC is the heat expelled at the cold reservoir. So the heat added was 4,000 joules, and the heat expelled was 2,500 joules. So the amount of work done is going to be simply 1,500 joules. So remember, two parts to a heat engine. There's a high temperature area and a low temperature area. Heat will be added to the high temperature area. We'll expand a gas and do a little bit of work, and then most of that energy will be expelled to the cold reservoir or the low temperature area. And for most engines and steam engines, that low temperature reservoir is the outside environment. And this is an example of applying the second law of thermodynamics. I look forward to seeing you in class tomorrow.